So now we're going to take a look at cable modeling, and this slide here shows the different sort of cables that we could have. Basically what we've got is, let me go ahead and just adjust the pointer on here. Basically what we've got is we've got what we call a concentric neutral cable. Concentric neutral is characterized by having for the neutral return wire a number of individual small conductors that are kind of wrapped around the main cable. They could be jacketed, where we have an outside covering. It could be non-jacketed. This could be placed in a conduit. We could also have what we would call more of a tape shielded type of a cable, where basically instead of having these individual conductors, we would just have kind of like a thin, kind of uniform covering around. If you look at really old cables, this is kind of a cutaway of that. You can see that this is a case where you have a three-phase cable, and instead of having kind of like more of a plastic insulation, this actually makes use of more of the paper insulated technology. So this would be something from, maybe like 100 years ago. And then another sort of cable, which isn't really a conventional sort of cable, but it's still a cable, would be if you have overhead, you can actually have what we call covered wire. And so the reason you might have that is if you have problems with trees touching your overhead lines, you might actually want to have a covered wire up there to kind of protect your overhead. So anyway, these are all sorts of different types of cable that you might actually see in practice. Just kind of getting into the construction characteristics of the single phase concentric neutral, because it's something we run into so often. See if I can jump back to the pen in this case. Yeah. So if we talk about a concentric neutral, the things that we have to be cognizant of is obviously you've got the conductor in the middle, right? And in this particular situation, this conductor is made of individual wire, right? So it's bundled in a way. And then what we have is we have an insulator. But the thing of it is, we don't want our wire rubbing up directly against the insulation. So what we do is we make use of what's called a shield layer. And so on top of the conductor, you'd have like this conductor shield on top of it. It would provide some separation between the wire and the insulation. This insulation is usually some type of a plastic compound. It's going to have insulation characteristics which are a couple times better than air. And then you'll have another insulation shield, and then you'll have these concentric neutral wires. And finally on the outside you have the jacket. The reason I'm pointing this out is if we're doing the modeling, this is going to depend on distance information as well. Specifically the distance between the center of this conductor and the wire. And in order to get the distances right, not only do you have to consider what's going to be the depth of this insulation layer, but also you have to know too, and what's going to be the depth of the shield layers as well. And so anyway, that kind of factors into our equations. As far as three-phase cable, I'm going to be looking more at three single-phase cable systems, but again, what you would have is you would have these conductors and they would have insulation. Something else you factor into these calculations is what would be the distance between these center points. This shows a cable which may not have a neutral return associated with it. But anyway, what you would have is you'd have some filler material in here as well in order to kind of make sure that the internal conductors are always like the same distance apart. So anyway, what we're going to be looking at is, given that we have like this characteristic information on the wires and in the spacing, then how do you do calculations for impedance? How do you do calculations for capacitance, just like we did for the overhead conductor? As far as these cables, a lot of times these values would come in manufacturer tables that look like this. When these cables are installed, say utilities were going to put these out in the field, typically what they would do is they would use a certain spacing. And so like the utility, when they would bury these, they would have like phases A, B, and C. These would be when they're using 3 single phase conductors. And then what they're going to do is they're going to have these cables spaced so far apart. And so if you're looking to make sure you have enough heat dissipation and other things, you're going to have a spacing between these cables. In this case right here, this would be kind of a standard spacing, 7.5 inches between adjacent cables. And what you could also get from the vendors too is you could also get this information as far as what would be the equivalent impedances. So they're kind of giving you the end result in a way. They would give you sort of like the positive sequence values, and they could also give you zero sequence values. And note they have a couple different configurations here. They have what they call full neutral, and they have what's called third neutral. And so if you're going to have a highly imbalanced type of load, where you know you can have a lot of current going back through the neutral, maybe to use a full neutral. Where in this other situation where you think you're going to keep the load fairly balanced, then you might make use of what's called a third neutral. So basically the difference there would be in the neutral wire size that you have available to you. But what we're going to want to have the capability of doing is figuring out, like, well, where do these values come from, right? So there's 2 general cases that we would want to be able to handle. We want to be able to handle if you have concentric neutrals, and also if you have like tape shields. Again, the concentric neutral case, what you have is you have these individual neutral return wires. Basically, each of these strands, you're going to have so many strands, like end strands, and each strand's going to have a diameter associated with it. What we'd have to track is we're going to have like the interphase conductor. There might be a little bit of a jacket around the phase conductor. There's going to be the insulation itself. There's going to be another jacket around the insulation, and finally this is where you have the neutral strands. And what we're wanting to make sure we get is we kind of know exactly what this distance is going to be. We'll also see, like in a little bit, that this is also going to be related to how many of these strands we actually have. For the tape shield cable, this is actually simpler to do calculations for. So you have the phase conductor in the middle. You probably have some type of shield there. You're going to have like your insulation. You'll have metallic tape shield around there that's going to factor into this. And what you would want to know then is not only would you want to know the information about the diameter of the conductor, but what's the diameter of this neutral. Basically, what's from the center point of the tape shield on one side to the tape shield on the other side. And then you could put these together in different multi-conductor configurations where the 3-phase would be most common. So here's a case where you have 3 concentric cables and you're going to have like a certain spacing. In this particular case, what you're going to have is you'll have different sort of distances, and what's going to be different in this case is now you're going to have a distance between the cables themselves, so DAB, DAC, and DBC. So they don't, a lot of times it would be laid out flat. This just makes it easier to draw. One thing about what I've got drawn right here is the question of what type of wire system is this? So before, when I was talking about overhead, I was talking about 4 wire systems. And so I got 3 phases and I got a neutral wire, right? So that's a 4-wire system. So all our calculations are based around that. For this particular system, how many wires, the equivalent wires, do I actually have? Well, I've got 3 phase conductors, but actually instead of having a single neutral, I've actually got 3 neutrals now. And so we would actually call this would actually be a 6-conductor system. And actually, to characterize this, I'm actually going to start off by having a 6x6 matrix. So it's almost as if you got phases A, B, and C for the phase conductor, but then you have kind of like an AN, a BN, and a CN for the neutrals associated with each phase. And so really what we've got in this case is we've got a 6-wire system. So for the concentric neutral cable case, there's formulas been developed for this, and I'm not going to go into the math behind it. But basically, you got obviously the GMR for the phase conductor, right? And doing these equations. We could actually apply the same equations that we had before, but what's going to be different? We can apply the same equations that we did for overhead, but now what we have to have is we have to have the appropriate GMR and distance information, right? The GMR for the phase conductor is just simply what you get from the table, but now if I have a concentric neutral, and if I've got all these separate neutral wires, then what am I going to have for the GMR or the equivalent neutral? Well, in this case, it turns out the GMR from the neutral is the root to the power of n, where n is the number of conductors you have for the neutral. It's just root to the power of n of GMR for a given strand times the number of strands times the diameter of the neutral wire divided by 2 to the power of n minus 1. And again, I'm not going to go through the derivation for this. But anyway, this is something that you could use in the same equations that you use for the overhead. The resistance in the neutral wire is just the resistance of a single strand divided by the number of strands. That's pretty straightforward. Then when you talk about the different distances, basically what you're going to have in this case for the appropriate distances, like if you're talking about the distance between a phase conductor, a cable I, and the concentric neutral for that same cable, that's just going to be the diameter of the neutral divided through by 2. As far as the distance between concentric neutral I and adjacent concentric neutral J, we're basically going to use the distance between the centers of 2 adjacent cables, make things simpler. And then one thing that's a little bit more complex, if you have a distance between a neutral of I and a phase conductor of J, that you have this other expression. It's kind of complicated to calculate, which is the root to the power of n of this distance term to the power of n minus the diameter of a neutral divided by 2 to the power of n. Usually what you're going to see is this term is going to be pretty close to this term right here, but there's going to be a little bit of correction depending on what the diameter of the neutral is. So anyway, basically what this enables us to do is use kind of the same types of equations that we use for overhead. We just have to make some compensation for what we're going to use for the different GMR and for the different distance terms between conductors. And again, this can kind of be viewed as a 6-wire system, and so we're going to actually have not only distances between phase conductors, but distances between neutrals to consider as well. The tape shield case is a little bit simpler in this case. Basically, we don't have to worry about the number of conductors, so this kind of shows the approximations we would typically make. And then one thing you would run into is you could actually have a case where you had a separate neutral besides the neutral just in the cables. And so that would make this a 7x7 system, and then we would have to eventually reduce that out as well as far as getting like an equivalent 3x3 matrix for this. As far as capacitance, capacitance is a pretty important term to include for cables of any length. And so just from a basic physics textbook, I mean, it's probably seen that this capacitance is 2 pi times the permittivity times the length divided by the natural log of B divided by A, where B is the outside diameter This would be where you'd have like your neutral at, and then A would be the distance from the center conductor. This is a function of relative permittivity, so maybe your typical value relative permittivity might be something like 2.3. And then once you have this value C, then you can calculate Y, where Y, this admittance, is J omega times C. As far as CAN formulas that you see being used, a lot of times it's convenient to get this in terms of per mile basis. And when we're talking about the inverse of ohms, that would be Siemens. And so if we're talking about a concentric neutral cable, then this equivalent admittance between the phase and the neutral is given by this particular formula here. I'm not going to try to say that out loud. But this is in terms of per mile. So we're actually converting from meters in order to miles for this. And then for a tape shield, you're going to have a similar type of a situation. So it's pretty similar to this equation right here. Now, one thing on this is you notice that we don't have any formulas for the admittance, the capacitive admittance between cables. Basically, the reason being that if I had multiple cables, say if I had like phases A and B, and if I had a center conductor, and if I had a neutral around here, basically what that neutral on each cable is going to do is it's basically going to kind of act as kind of like a Gaussian shield to keep the field from emanating outside that cable. And so we are going to have like a capacitance associated with the single phase cable, but then we wouldn't have any type of mutual capacitance like we would have for like an overhead line. All right. So we just basically have kind of like the cable, the single phase cable capacitance, but there's no mutual CAB type of term that we would have unless we didn't have this neutral on the cable. But most of the time you're going to have the neutral on there. So that's why you just simply have this IPIN type term. There's no IJ types of terms here. All right, so in the notes here, I got an example for doing these calculations on a single phase. I'll have to maybe dig around to see if I've got any three-phase examples. That might actually be in the notes. But this is a much more involved calculation than what we would have for doing overhead. And so what I'm just doing in this simple example is just kind of showing how you would do this capacitance calculation for a single phase cable. And again, it's a two-wire system. So it's got the conductor and it's got the neutral associated with it. And so what we're going to do in this case is we're going to assume I've got this cable, and this is the center conductor, and what we're going to assume in this case is it's grounded at both ends, and it's actually grounded through earth. And so what we would need to do is we would need to take this earth return into account as well. In other words, not only can the current return through the outside neutral, but it could also return to the earth as well. And so anyway, you go to the cable tables and you pull these values out. And again, what you have to take into account is not only the diameter of the wire itself, but then other things you would enter in would be, well, what's the diameter over the insulation, and you include the screen, and then you look at the outside diameter on the outside of where the neutral wires are at. But all that stuff would have to be possibly factored into the calculations. In this case right here, also what you can kind of see is for the neutral, you've got 13 strands of number 10 American wire gauge wire. So anyway, this just kind of relates this to this particular diagram I showed before. And so as far as the calculations, then you would have this conductor diameter, and then what you would do is you would take into account, okay, what's the insulation depth you have and any sort of additional jackets you would have. And then what you would want to do is you would want to basically be able to figure out what's actually going to be this distance right here, right? And that may not be given directly to you, which is why you would get this information, you get this information, and then use that in order to figure out what actually the diameter is associated with the neutral strand wires themselves. As far as the conductor data that you would have, you want to get for the conductors themselves, you want to get the diameter information, the GMR information, you want to get the resistance information as well. And again, we've got a 4/0 in the middle, and then we've got these 10 AWG neutral wires, these concentric neutral wires. And then what you would do is you would calculate the equivalent distance information and also the GMR information. And so again, notice what I had to do on here to get the distance between the phase and the neutral is I had to take that outer diameter and also that inner term over the shield, and then I had to take the difference between those two in order to get the information I wanted for this distance between the phase and the neutral. Use this equation for getting the GMR, the equivalent neutral. And then really all I'm doing in this case is I'm just using the same formulas that I used before. So again, this is exactly the same formulas that I used for overhead. That's the whole point of these equivalent values. So again, since I got the neutral connected to earth, I'm modeling the Carson's correction in here. Okay, I'm using the GMR, the phase conductor. For my neutral, then again, I've got the neutral resistance, I got the earth effect, and then basically I'm including the earth effect. I've got this equivalent GMR to get the self-impedance of the neutral wire. And then I've got a mutual coupling term here as well that involves this distance between the phase and the neutral wire. And so once I've got this, I get this kind of this primitive impedance matrix, that includes the neutral. And then what I can do is I can actually, just like I did before with the overhead, I can do the chrome reduction and basically eliminate that neutral wire. And then I just simply get an equivalent value that I could use for a per phase calculation. And so you can go through similar steps then if this were like a three-phase set, but you can kind of see here that's going to be pretty complicated to do. As far as the admittance, then we could use the formula relationships for a concentric neutral cable. So again, I got to get this appropriate diameter for the neutral. I've got the phase information, I got the diameter of the strand, and so I can plug this into this formula for admittance. And what I get here eventually for this admittance is J96.11 microsiemens per mile. And again, this really wouldn't make any difference if it were single phase or three phase, because you don't have any mutual coupling in a three-phase set. So what I would have for the admittance matrix, in this case for 3x3, I would just simply have these terms on the diagonal. I wouldn't have any off-diagonal terms in this case. Okay, so anyway, this is what I got for the cable modeling. The reality is you may not do too much of this sort of calculation. Again, there's a lot of programs that are available for doing this, and I'll show you in the next video segment some examples of what these programs look like and the sort of data entry that you need to apply. For doing these calculations, a lot of this material is out William Kirsting's book on distribution. This is available as an ebook in the library, at least for the 2004 edition. And so he actually goes through a lot of the details of where these impedance and admittance calculations come from for both the overhead and then the cables. Another reference for cables and also for overhead and line modeling, especially in EMTP, would be there's a set of books by Amitani. He's got a first and a second edition of this Power System Transits book. This is the date for the first edition. He's also got a book on just cable modeling. And the significance of this would be Amitani, he's probably in his 70s by now. But when he was working on his PhD in the 70s, that he actually was a contributor to the original EMTP code. And he actually provided a lot of the cable modeling. In fact, they call this like the Amitani cable model, right? So he did a lot of work on this early on, and he still did some follow-up papers on it. So if you guys really want to get into more of the detail on the cable modeling or the line modeling, you might want to take a look at this book. This book's available as an ebook in the library, and it gets into just a lot of depth on doing the cable modeling. And they get into like the multi-frequency modeling, and which could be important for certain more advanced types of situations. But the stuff he gets into this book is kind of way beyond what we can kind of hope to cover in this class. But if it were important to get into more advanced line modeling, to get access one of these Amitani references would be pretty good, because he was the guy who came up with a lot of the early cable models in the first place. All right, so what I'll do next is I'll pull up some examples in PSCAD and Simulink and just kind of show you just kind of what the data entry would look like for putting in this line models if they're lump models, and then what are some of the available tools for doing these impedance and admittance calculations.